Hello, I'm Mari Silbey, Director of Communications for US Ignite, and part of the Project Office for the Platforms for Advanced Wireless Research, or POWR program. I'm joined today by Dr. Thyaga Nandagopal, Deputy Division Director for the Division of Computing and Communication Foundations at the National Science Foundation. And we're here to talk about a new project just announced that's being funded by the Department of Defense and will use one of the outdoor city-scale test beds in the POWR program for ongoing wireless spectrum research. It's good to see you, Tiago.
Nice to see you too, Murray.
Conversations about this project began after DARPA's Spectrum Collaboration Challenge wrapped up last fall.
Mhm.
Why do you think the DoD wanted to fund efforts to continue this particular spectrum research after that competition ended?
So for those who may not be very familiar with the DARPA Spectrum Collaboration Competition Challenge, it was a competition that was launched where uh, they wanted to break the traditional assumptions on how spectrum should be allocated when you had an option to give multiple users an opportunity to use spectrum in a given band however they wanted without creating defined boundaries between different users. So they try to test this strategy using novel techniques or such as artificial intelligence and other optimization tools. And they tested it using a customized emulator that they built specifically for this competition. Of course, the emulator worked well, and the competition showed a lot of promise for this so-called free-form collaborative allocation of spectrum resources. And DARPA is very excited that this actually shows some promise. And of course, clearly, once you have shown this in a test environment, you obviously want to take it to the next step and say, will this work in the real world? And the DARPA was looking for a place to demonstrate this. And at this time, we at NSF, who had been working with DARPA as partners on the Spectrum Collaboration Challenge, essentially pointed to them that we have a fantastic test bed at Salt Lake City that is ready to go and could be used to test this particular concept. And this is exactly the kind of advanced research users that the platform was designed to support. And DARPA got very excited. They talked to the PIs of the testbed, and they were eager to continue and take the winners from this particular challenge and ask them to implement their solutions in a real life use case using the CBRS bands that are being used for, are proposed to use for 5G. So the concept now is they will demonstrate the same concepts of how do you share spectrum without predefined allocations across different types of entities in a 5G-like environment on a real network in a real life setting in an outdoor campus-like environment. So that's what I think got them excited. The fact that we had them ready to go and it matched their future-looking expectations.
Yeah, so talk a little bit more about that and sort of the role of these outdoor test beds, which haven't really existed before now, at least not at this scale. What do you see as the role for these test beds going forward with 5G and other advanced wireless network technologies?
Right. So when we conceived of this test beds back in 2017, there was a heavy clamor from a industry that while they were investing in many of these 5G test beds, it was clear that the industry test beds were very focused on a specific deployment use case, and the entire design space of 5G was so vast that even the folks in industry and of course in academia felt that even with all the resources they had, they still wouldn't be able to conceive of different kind of customized test beds to meet every possible design challenge that a 5G network would be conceived for. So the suggestion that the feedback that we received from many of our industry partners and collaborators, as well as from many of the academic researchers that we fund at NSF, was that how about we create a flexible, highly programmable test bed that can be used as a proof of concept for testing some things that we have never dreamt about. And this is essentially the genesis of the Platforms for Advanced Wireless Research program. And we decided that we will fund 4 different test beds addressing 4 unique aspects of the ecosystem, right? So one of the aspects is how to take the existing spectrum that within the sweet spot of up to 6 to 7 gigahertz and see how can you manipulate and play with the spectrum in a dynamic sharing environment. So that's the test bed we have in Salt Lake City. The other test bed was kind of designed to thematically focus on higher order spectrum, which is the millimeter waves and beyond. And that's a test bed that we have all funded in New York City. And the third the third platform was looking to test novel uses, including autonomous cars and autonomous mobility vehicles. So this is a test bed that we are funding in Raleigh, North Carolina, that's focused on drones and autonomous vehicles in general. And we are still in the process of working through our fourth test bed, which addresses a very important but often overlooked piece of this broadband puzzle, which is rural broadband delivery. So we designed these platforms to address these different pieces of what we think are potential 5G use cases. And each of these are deeply programmable and highly flexible to customize by users with varying levels of expertise. It can support somebody who wants to come in and simply use a 5G network to send data or run a specific application, and also support an expert user who wants to tweak a particular radio for doing a certain types of optimization and see if the 5G network can accommodate it and what kind of performance gains they can get. So we have designed this platforms program to accommodate all kinds of users, and we have opened it up for use by industry, by academic folks, researchers, as well as federal agencies and anyone else who might be interested.
Now, one of the things you kind of explained there is the fact that there are so many pieces of technology that are part of where wireless networks are going forward. And you've set up these test beds, or the test beds are set up to address a number of these different aspects of wireless networking. Why is spectrum sharing in particular such a hot topic, and why is that so important for the way we think that networks are going to evolve?
I think that you're asking a very important question. And the way to think about this is, when we started using networks for data, like your typical cell phone that we use today, it has a 3G. It used to start with a 3G network about 10, 15 years ago, when the amount of data bandwidth, the bandwidth allocated was close to 20 megahertz per carrier that was in operation in the United States. When we went to 4G, we got a higher bandwidth for sending data and so forth. That was still about 100 to 200 megahertz, no more than that. So we clearly are hitting the boundaries of what we can do with this kind of bandwidth. And often the solution is seen as, if you give more spectrum, you can send more data. That's an easy fix in some sense, an easy way of scaling from your phone being able to receive 100 megabits per second to getting 1 gigabit or even 10 gigabits per second. This is the promise of 5G. But where does the spectrum going to come from? And that's a challenge, right? The optimal spectrum that you want, the sweet spot, is in what we think of as the 1 gigahertz to 6 gigahertz, or slightly higher above that. That's the sweet spot. But that spectrum has been sought after by multiple parties, and therefore it's highly contested. Everybody claims primary use of different portions of the band, but because we understand the economic value of these advanced communication networks, the federal government has been taking a much active role across different administrations to open up more and more bands for telecom users. And therefore, instead of taking away spectrum from an existing user and giving it away to a telecom purpose, they're encouraging users to share spectrum, right? So if I'm not going to be using the spectrum all the time in every place in the country, why not think about sharing that spectrum for telecom purposes? This requires users to collaborate. Verizon will have to talk to, let's say, a satellite provider to say, are you using this now? Can I use this now? And if they say yes, they'll go ahead and use it. So you could do different types of sharing. So the federal government has been pioneering this with sharing of spectrum between Navy radar bands and with commercial LTE providers. And this has been highly successful. And therefore, they see this kind of sharing as the future. But in order to make it work, You need to understand the needs of the different stakeholders and test the different scenarios that come up. What are the power levels that are acceptable? What will cause interference and what will not cause interference, right? So, and what kind of devices are permissible to transmit? Will my commercial radios interfere with my specialized radios I have for this other specific national security or safety application? There's a lot of things that need to be tested, and this is why spectrum sharing is an important frontier to help advance the next generation of broadband networks.
Now, what you alluded to there is the importance of spectrum sharing and wireless networking for a number of different federal agencies. And there's a lot of work and research and development work that's happening from these agencies, but there's also obviously a lot of work that's going on in academia and also in the private sector. So where do those segments overlap, or where should they be overlapping?
Right. So of course, the federal government is trying to open up a lot of the spectrum that it has. The U.S. government across all the different agencies has claims of primary use for very large amounts of spectrum in this sweet spot. Now that they are willing to open up, but they don't have the resources to investigate how best to share this. And this is where they're relying on private industry and academia to tell them, to do the research and tell them how best to share. And of course, they are going to conduct their own validation and verification of these studies, but they are relying on other stakeholders to be the leaders in this space. And NSF, the building that you see behind me in the background, has been funding such sharing research for over 15 years now. And much of the research that we have funded in the past has proven highly useful to the agencies like FCC in deciding, yes, sharing in certain models actually works. And that's the CBRS sharing, for example, is something that is a direct outcome of funded research that NSF supported, probably 15 years ago. And we have similar successful outcomes from the research activities undertaken by academics as well as private industry that have informed how such sharing can be done. And this is exactly what we are trying to accelerate, right? So previously it used to be companies that are trying to do this on their own volition. And of course, they would have to figure out how best to test this. And the challenge with testing often comes from a company says that, oh, here's the testing that I did on my network, and this is why it's beneficial. And the other stakeholder may say, well, it's your network. You are trying to maybe bias the results. Maybe it's your way of measuring that may be flawed and which I may not agree with. So how do you do this test in an unbiased location, in an unbiased manner? Can we have common standards that we can all agree to? Some of that stuff is what we are trying to address with the PAWR program, right? So this is a common place where both multiple stakeholders can come together and say, we see the testing environment, we agree that it's of high caliber, and let's try to agree on a common test framework. Let's measure it. It doesn't matter who funds the study, right? You are going to get unbiased data, and that unbiased data can help make important and critical and appropriate policy decisions that will be beneficial to all the stakeholders at the same time.
Now, the research project that we're talking about specifically, the Xylenium team that's going to be moving their research onto the outdoor wireless testbed in Salt Lake City, you've alluded to the fact that they'll be using an AI-driven engine, which was sort of part of the focus of the SC2 competition, the use of artificial intelligence to autonomously allocate spectrum resources. How important do you think future AI technologies are going to be to the evolution of telecommunications networks?
Telecommunication networks, just for context, have been largely governed by a manual process of relying on human knowledge to optimize different parts of the network. This starts from trying to understand how signals travel across buildings and terrain to configuring a network to say this is how much frequency that somebody needs and this is the bandwidth that they're going to get under certain conditions, to setting up network parameters to say, what kind of priorities should traffic get at different times of the day. It's a highly manual process, and by some estimates, to our typical network that we all are used to, your 4G network that we all use today with our iPhones and Android phones, has around 5,000 parameters that somebody has to optimize. And it's often is not very optimally done. And early studies using artificial intelligence techniques to optimize some parts of the network have shown significant gains, sometimes as much as 30 to 40% gains by just optimizing some portions of these parameters. So this is why we believe the artificial intelligence can be a vital tool in helping explore the vast design space that wireless networks currently operate under. And the SE2 competition specifically highlighted one critical aspect, which is the process of assigning spectrum, which is once you assign spectrum using a predefined allocation, this is the only amount of bandwidth you're going to get, no matter how long you want to operate or whether you have something to transmit or not, regardless of how many people are competing for it. Once you get your allocation, you get to keep it and nobody else can use it. It locks up the frequencies. And what the Xylenium team is trying to do, and this is what the Spectrum SE2 competition was trying to do as a whole, was can we use AI to make these decisions on the fly, right? So a carrier can come and say, assuming this goes into practice in the commercial world, a carrier could say, I am experiencing heavy demand from many of my users who happen to be in this area. Can I use more spectrum? And other carriers say, well, yeah, I'm not using it. Why don't you use it? And in exchange, there is some way of making sure that their services are recognized for transferring and sharing spectrum. Operating together for the common good of making everyone's performance better is the goal of this particular competition. And AI is a very important tool to making sure this happens. So that is what the thing that we are trying to test. And I think this has a lot of potential, not just in spectrum sharing, but also in other domains of wireless.
So just to close out and very briefly, we've touched on a number of different topics here. What do you think that the nation as a whole should be doing to promote advancements in communications technologies, and where do you think our top priorities should be?
I think the nation has to do a lot to advance the state of communication networks today, and administrations past, present, and hopefully the future, I think, are keeping their eye on the ball to do so. I would specifically call out attention to two documents that have been recently produced that by the federal government. One is the strategy to advance R&D priorities in wireless spectrum. So this was issued around this time last year. So this document tries to identify the key R&D activities that needs to happen to ensure spectrum is used well and efficiently, which is a critical piece of having an advanced wireless communication network. The second piece of this puzzle is the networks we have, we need to make sure that they operate well and they are secure and they are robust. Why? Because we are talking about 5G networks taking on important roles in telemedicine and safety critical applications like advanced manufacturing and remote operations of vehicles, autonomous vehicles. So for these networks to operate the way they're designed to operate in these critical scenarios, these networks have to be secure and robust. And the administration, the Congress and administration have recognized this need, and this is why the Congress passed a law called the Securing 5G and Beyond Act of 2020, which was passed just recently. And this calls for ensuring secure 5G and beyond networks that we have in the future. So these are the two critical pieces, making sure the spectrum that we have, which is generally a scarce resource, is used really well, and making sure that the networks we do design and deploy are secure and reliable and robust, as well as, of course, operating at high performance and efficiencies that we expect networks to operate in any way. So these are two important pieces. And the missing piece, I mean, in some sense implied in both of these, is we have to continuously invest in advanced research and development to look out for the frontier of what we do not know yet, right? So spectrum sharing is one of those things. Now, there are some accepted models of spectrum sharing. There are many more models that have not been explored, right? Advanced spectrum going into millimeter waves and terahertz is something that we have to really explore, right? New hardware and software techniques. We're talking about conversion of hardware-heavy ecosystems to a software-defined network that is flexible and agile and is able to deploy more features quickly. So this is another piece that's really needs to be worked on. And at NSF, we are funding several programs, including a very recent one called the Spectrum Innovation Initiative that is trying to address many of these R&D gaps. And we believe we need to keep doing more of this because we are not going to stop here, right? So the world is going to consuming more and more information. And in order to support this information demand, everything is wireless, and therefore we need advanced communication capabilities that rely on advanced wireless networks to deliver this information and meet this need. And this is what we will continue to do, and the nation as a whole, across the private sector and academia and the federal agencies, have to keep this focus as they move forward.
Great. Well, we're going to close out there. Thanks for the insights. For more information on today's news and the Platforms for Advanced Wireless Research Program, a $100 million public-private partnership funded by the National Science Foundation and 35 leading wireless companies and associations, please visit www.advancedwireless.org. Once again, thank you for joining us. Appreciate it.
Thank you, Marie. Nice to see you.